Okay, welcome back. We are still in section 2.5 linear operators, where we have learned all about bounded linear operators, starting from what a bounded set is up until operator norm, properties of the operator norm. Okay, and then the set of all bounded linear operators turning out to be a space, even a normed space, and sometimes even a complete normed space, also known as a Banach space. Next thing in that section 2.5 is compact operators, but before we can speak about compact operators, let's get one step back and talk about a certain class of sets. And for this we go back into a metric space. So let X together with D be a metric space. And let's look at, for simplicity, a finite subset S of X be finite. Okay, so just for example, if this is our space X and here's our subset S, then we could say that our set S consists of just three elements. There's the red element, the blue element, and the black element. And now what we're going to do is to look at sequences of elements in S. So let's take sequences x1, x2, x3, and so on, where every element is in S. So in our example, such a sequence could be red, black, black, blue, red, blue, blue, black, red, blue, black. Well, you know, it's an infinite sequence, so it's a never-ending long sequence of blue, black, and red in some order. But what we can certainly say about that sequence is that there exists a convergent subsequence of our sequence xn. Well, in our particular example, or in every finite set example, there is even a constant subsequence of xn, because if you only have three colors and infinitely many elements in your sequence, then infinitely many of them must have one color, and then you just pick that subsequence, which is going blue, 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 blue all the time, assuming that blue has been picked infinitely many times. But at least one of the three color classes has to be picked infinitely many times, because otherwise you couldn't get infinitely long sequence. Okay, let's denote this property without the blue even constant bit by star. And that is clearly a property of the set S. And here's already our first definition. We say that a set S is relatively compact, or some books prefer to say pre-compact, if the property star holds for S. So first immediate consequence of this definition is lemma 1, finite sets are relatively compact, because this is what we say here, right? We say when you're a finite set, then you're subject to property star, and that's exactly what we call relatively compact sets here. By the way, if you hear someone speaking of a compact set, then they have the same definition, except that the limit of that subsequence here is also assumed to be in the same set S. If you don't assume that, then you don't say compact set, then you say relatively compact set. Okay, and here's already a next little lemma. Relatively compact sets are always bounded. Well, that's clearly a bit more interesting than the previous lemma. Let's give it a little thought. So if S is relatively compact, then every sequence of elements from S has a convergent subsequence. Now it's actually easy to see that convergent sequences are bounded. So every sequence of elements from S has a bounded subsequence. From here, it's actually not difficult to conclude that the set S is bounded. Give it a little thought how you would fill the gap in this proof. I'm sure if you think long enough you will find how to fill that. It's not very difficult. Well, if you want, we could also discuss this in the problem session on a Monday afternoon. Okay, remark. I've written lemma 2 with this implication arrow so that it's easier now to speak about the reverse implication. Let me say often also the reverse implication holds in lemma 2. Okay, now what does often mean? Let's give examples. A first and simple example is x equal to the set of real numbers. So here's the real line, and the statement is as follows. I'm claiming that the reverse implication holds in lemma 2. So if you have a bounded set on the real line, then that set is also relatively compact. Well, maybe you recognize this statement as the Bolzano-Weierstrass theorem from your Analysis 1 course. So let me remind you of the idea how to prove that. Well, if S is a bounded set on the real line, then you can surely squeeze it into an interval, let's say from A to B on the real line. Okay, and then we have to convince ourselves that our set S is relatively compact. So to see this, you take a sequence of points from S. They will then also sit inside our blue interval AB. And that sequence is infinitely long. So I'm throwing infinitely many red points at that blue interval. What you will observe is that, well, if you throw infinitely many red points into that interval, then in one of the two halves, there will still be infinitely many points, because otherwise you would only have finitely many points at all. Let's continue with that half. In this case, it's probably the right half. At least it looks like it. I didn't exactly draw infinitely many points, but you know what I mean. Let's again divide that in half, and then again in one of the two halves there are infinitely many points, and that one we again divide in half, and then in one of the two halves you have infinitely many points. Again divide, 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 ending up with smaller and smaller intervals that still contain infinitely many points from your sequence. That's how you find so-called accumulation points or partial limits of your red sequence, and by showing your red sequence has an accumulation point or a partial limit, you're showing that it has a convergent subsequence, and hence your set S is relatively compact. You can easily show that the same effect also holds if you go to R2. And to see this, you could either argue component-wise by taking a sequence of two vectors that is bounded, and then showing that this is a convergent subsequence as follows. You just conclude that its sequence of top components is bounded in R1, and its sequence of bottom components is bounded in R1, and then use our Bolzano-Weierstrass theorem for the R1 case, saying that, okay, from this bounded blue sequence you can extract a subsequence that converges to something. Let's call it x sub 1. Okay, and then just restrict consideration to that subsequence, and for that subsequence, of course, the lower sequence is still bounded, and hence, again, by Bolzano-Weierstrass has a convergent subsequence. Okay, and now if you're in that subsequence, then also the second component converges to something in the real line. Let's call it x2, and then put these two together, and indeed you get convergence of your sequence. Another way to see it is like this. You argue that any bounded set in the plane can be squeezed inside a square. Then take an arbitrary infinitely long sequence of points from your set and start dividing your square. And now, because this is 2D, you divide it not in 2 but in 4 parts like this. And then, because in total you have infinitely many red points in one of those 4 quarters, there must still be infinitely many red points, and then split that again. And continue as we did in the 1D case. And so on. I think you're getting the idea, and you can almost see the accumulation point. Having seen the argument for R2, I think you won't be surprised that the same works for every other Rn. And because it works for R2, it will also work for the complex numbers, and then it will also work for Cn. Okay, I think you're getting the idea. Well, in fact, the following lemma holds. And for this lemma, we have to go to normed spaces, no longer just metric spaces. So for normed spaces X, the reverse implication holds in lemma 2 if and only if, so we often abbreviate lists like that, the dimension of X is finite. So all the examples we have seen where the reverse implication holds are finite dimension examples, and in fact it has to be so. And for infinite dimensional norm spaces, the reverse implication does not hold. So in order to better understand this effect, you just have to envisage the following experiment. So take a bounded set, so maybe a cube or a ball, and try to put infinitely many points inside without them accumulating anywhere. But we know from Bolzano-Weierstrass that this is impossible in 2D, 3D, and so on. But we just gave the proof. So how can we understand this? So if you want to avoid accumulation, you could conversely ask, how many points can I fit in here without them coming into a distance from each other of less than 1, or in corona times you could say 1.5 meters. Okay, so let's assume this is the unit ball, and you're trying to place as many as possible points here that have distance at least one from another. So one could be here at the origin, then one could be on the boundary, then the next one could be like here at the earliest, so that these form a triangle with all sides equal to length equal to 1. Okay, then number 4 could be here, number 5 is here, and finally number 6 and 7, all forming these nice triangles which have all sides of equal length. Well, you know that in such a triangle all angles are 60°, and because 360 just divides so nicely into 6 times 60°, we know that this circle we've been drawing here is exactly closing after 6 points sitting on the boundary and 1 in the middle. Okay, so in R2 we can put exactly 7 points inside the unit ball so that each two from another keep the, let's say, corona distance of 1 unit, which could be 1.5 meters. Well, let's not forget about R1. In R1, the unit ball is just the interval from -1 to 1. And if you want to place points here with distance at least 1 from one another, then clearly 3 is the maximum number of points that you can fit in. In R3, I believe the number is 13. And I have no idea what it is in R4, but it's certainly a finite number. If you don't like this whole idea of points in the unit ball keeping distance at least 1 from one another, you could also think of closest packings of balls that have radius 1/2, like this. Okay, and now imagine this 2D situation here, and instead of 7 circles lying next to one another, imagine 7 balls in 3D lying in one plane on top of your desk. And then if you want to lift the situation up to R3, well, you could place additional balls. For example, one could be placed on top of that ball in the 3rd dimension. Another ball could be placed just below that one, also in the 3rd dimension, but below your desk. And that's how you can see that in R3 at least 9 balls would fit, touching each other without coming closer than distance 1, speaking about the midpoints. Okay, but in fact the number is 13, and you have to wiggle a little bit, and then you see these 13 points. But my point here is that by increasing the dimension, you can always increase that number of points or that number of balls. And that's kind of how you can see that by going up to an infinite dimensional space, you can fit infinitely many points there without having a distance less than 1 from each other, or to say it differently, you can put infinitely many points inside the unit ball of an infinite dimensional space without them accumulating anywhere. Okay, to finally convince you of this fact, here is an example. Take x equal to L2, so we have infinitely long vectors and we are measuring in the 2 norm, and our set S consists of the so-called unit vectors. Let me call them En, where n is running through the natural numbers, and En is the vector that has zeros everywhere except a 1 at position n. These are clearly infinitely many points. How do we see this set is bounded? Well, the norm, and hence the distance from the origin of every En, is just the square root of a sum of a whole lot of zeros squared plus 1 squared, and then zeros again, which is 1. So this is clearly bounded. They sit on the boundary of the unit ball. But nevertheless, if you measure their distance from one another, so for example EM and EN, how far are they apart? Well, one of them has the one at this position, the other one has the one at some other position. So you would have the norm of a vector that has 1 here and a -1 at some other point and zeros everywhere else. And if you compute that norm, you would just get root of 1 squared plus -1 squared, which is root of 2. So they are certainly one unit apart one from another, and you have infinitely many of them. Okay, so much about relatively compact sets. Every finite set is relatively compact. Every relatively compact set is bounded. In finite dimensional normed spaces, also every bounded set is relatively compact. So in this world, the two words just mean the same, but not in infinite dimensional spaces. There they are different.